Daniel for this invitation. And it's my pleasure to be there at the PI once again. And I would like to thank the PI for invitation and for giving me the opportunity to lecture at the PSI program. So today I'm going to give an overview of a quite old subject, which is gravity, quantum gravity. Oh, yes, sorry. No, it's OK. It has to be higher. Yeah, it was. OK, that's fine. OK, so it's gravity, quantum gravity in 2 dimensions. So this will be a very general view of some aspects of this subject. And I've tried to make this accessible for people not from high-energy physics or string theory or mathematical physics and quantum gravity, so also accessible to condensed matter people or real high-energy physicists, if there are some in the audience, and especially for the students, young people. And so the first part of the talk will be a very partial and overview of quite standard old results. And after that, the second part will be a very short overview, but of some more recent and active question where I've been involved into. So why quantum gravity? So quantum gravitation, if you ask anybody, he will tell you that general relativity, the Einstein-Hilbert theory, is trivial in 2 dimensions because the G mu nu tensor is identically 0. This means that any metric is a solution of the equation of motion, or no metric if you have a cosmological constant. And that's because because the Einstein-Hilbert action in 2 dimensions is just a topological invariant. So it doesn't change if you make a change in the metric. However, in the quantum theory, things become much more interesting. And the reason is the veil or trace anomaly. So in fact, the subject really started when Sasha Polyakov in 81, he was interested by string theory, and he was interested in constructing a path integral, or if you want, a Feynman path integral, an integration of all the metrics with just the usual Einstein-Hilbert action. So there is a cosmological constant term, that mu, and then this topological term that would correspond to the Einstein-Hilbert usual action. And the motivation was to quantize the bosonic string that at that time was not very well understood. And he uses the fact that you have to gauge fix the diffeomorphism invariance of the manifold of which you are interested. And he proposed to use what's called the conformal gauge. That's the standard results that come out from the mass of the uniformization of Riemann surfaces. And it says that you can always find, for given any fixed reference metric that will be a classical metric, this quantum matrix, if you want, can be, in general, be made as proportional to some conformal factor times this reference metric, which is in general fixed, up to some fixed moduli. And for instance, for simple Riemann surfaces, the sphere has no moduli. G is a metric with constant positive curvature. The torus, the reference metric can be taken to be the flat metric. But then you have two moduli that are the aspect ratio. And in general, for a Riemann curve, what's called genus G, so G handles, you have 3G minus 3 moduli, and you have a constant negative curvature metric on this surface. Okay? So, as usual in quantization of gauge theory, gauge fixing involves the Faddeev-Popov term. This is a determinant of some differential operator that comes out from the theory. And computing this determinant, you get some effective action. And this effective action will depend on the metric we started from, namely on the conformal factor. So, if you write the conformal factor, I realize that, in fact, phi is the logarithm of the lambda. And then, if you write this, the effective action can be computed through the variation of the conformal factor, which is proportional to the trace of the stress energy tensor in the metric. And this is proportional to the curvature, the scalar curvature, times the coefficient, which is the central charge of the system of ghosts and anti-ghosts that appears. So some calculations that has to be done gives the number minus 26. And from this exact result, we tell you how the effective action vary with the field. You integrate this, and you get the effective theory for the conformal factor. So here, this effective action is just the Liouville, called the Liouville action. There is an unusual kinetic energy term for a scalar bosonic field. There is a term that is a linear coupling between the conformal field and the curvature with a constant that is, coupling constant that is called Q. And then there is the cosmological constant term. And with this normalization, the quantum metric is just E gamma phi. So phi is the logarithm of the metric tensor. And Q is related, the coefficient Q has to be related to gamma by this relation for reason of conformal invariance that I'm going to discuss later. So why is this effective theory called the Liouville theory? That's because in the classical limit, when gamma becomes very, very small, the equation of motion becomes the Liouville equation. So the curvature, the total curvature of this quantum matrix plus mu is equal to 0. So the solutions are metric with constant negative curvature. And Joseph Liouville in the 19th century studies the equation that defines those surface with constant negative curvature. Okay, but now here R depends on phi. Okay, so the main point is that the Liouville theory is a conformal theory. Namely, it is invariant under change in the system of coordinates that takes this form on the sphere, for instance. Why is it a conformally invariant theory? Well, when one studies critical systems in 2 dimensions that are described by standard conformal field theory, conformal invariance comes from scale invariance, rotational invariance, plus some unitarity constraints. For instance, the field theory, the continuum limit of the Ising model is described by a CFT because of scale and rotation invariance. Well, other conformal field theory are the 4-dimensional gauge theories that are conformally invariant that are studied in the ADS CFT correspondence. So here the conformal invariance on the 4-dimensional space-time comes from the symmetry of the ADS5 space that is in which the gravitational and string degrees of freedom stay. Okay? In Liouville theory, that's a bit different. Conformal, what remains of the diffeomorphism invariance after conformal gauge fixing is precisely this global conformal invariance. So it's a remnant of the diffeomorphism invariance. Okay? Okay, so Liouville is a CFT. So in general, a 2-dimensional conformal field theory is characterized by the number that is called its central charge. And in the Liouville theory, it is given by this formula. And the Vein anomaly consistency condition states that the central charge of the Liouville sector plus the central charge of the ghost plus the central charge of other fields, that if there are some fields that are coupled to gravity, it has to be equal to 0. And this gives the famous relation between Q and the central charge of the matter, okay, and the transformation law of the field. So it's a CFT with a known central charge, but it is called what it is a non-rational CFT. So in fact, it is a CFT, a conformal field theory, that is much more difficult to study than the ordinary CFT that people did for instance, application of CFT to condensed matter and statistical mechanics. Okay, so now let me introduce another part, which are the observable of the theory. What are the local operators of the theory? Well, beyond the stress energy tensor of the theory, there are the so-called vertex operators, which are basically exponential of the Liouville field with some coefficients that can be complex or real. In UV, it's real. And the conformal dimension, namely the way this operator transforms under conformal transformation, that's the analogous of the scale dimension of an operator in ordinary field theory. This dimension is given by this formula. So there is a Q. And in particular, the interaction term, the exponential of mu of gamma phi, has dimension 1. but you shouldn't think as mu as a mass term, because the theory is always conformally invariant, even if you add this term. Okay. So now you see that if you add a vertex operator in the functional integral, it amounts to insert some curvature singularity in the action. So you should view the insertion of a vertex operator to insert a conical singularity on your metric with a relation between, so this is the total angle of the conical singularity. This is a relation with the total angle of the singularity and alpha and the coefficient. Okay? Okay, so now here comes a bit subtle point. You should note that since the solution of the Liouville equation of motion are constant negative curvature, the sphere is not a solution, which seems a bit strange. In fact, it means that the partition function of the sphere is 0 because of some additional gauge degrees of freedom. But when you compute correlation function, so expectation value of products of vertex operator, these objects are well defined in the theory, provided that they satisfy what's called the Seiberg bound, which is first a bound on the alpha I that has to be less than Q, so that the angles here are positive and not negative. And second, the sum of the alpha I has to be greater or equal to 2Q, so that the sum of the curvature defect can be compensated by a negative curvature. Okay. So these objects are well defined, and these are the objects that play a very important role in the application of Liouville theories, for instance, in string theory. Okay. Why string theory? That's because the Liouville theory, in fact, describes also strings. In fact, it was soon realized that a Liouville theory describes a two-dimensional gravity, so some kind of string propagating in a gravitational background described by a metric, a tachyon background, and a dilaton field. But in the Liouville theory, so it's different from the ordinary 26-dimensional bosonic strings. Here, you can view the Liouville field as one of the coordinates of the space in which the string propagates. So you have the ordinary space plus the Liouville field. So it plays a role, for instance, of time. And the term, a term like I hat the curvature times phi of x, correspond to q x naught. So in fact, the Liouville interaction term corresponds to having a string propagating in a dilaton background that is linear in this time. And similarly, the coupling term, the interaction term, corresponds to having a string propagating in a tachyonic background that is exponential. So we have tachyons, namely a scalar field background, which is exponential. So it's a string propagating in a non-trivial background. Okay. So there has been many, many development of this aspect of Liouville theory that I'm not going to describe here because it's not the subject of the talk. For instance, 10 years ago, Nakayama made a very good review of what went on in Liouville theory for the last 10 or 15 years. There were already many references. And since then, there has been many, many more development because Liouville theory is connected to brane theory, in string theory, in M theory. When you consider string Liouville theory on a disk, so an open string. And there is also a relation that has been discovered more recently between the Liouville theory and supersymmetric gauge theory in 4D, and that's called the AGT relation and the AGT conjecture. And since the G is here, you don't need to talk about that. Okay. So this is for the continuum formulation of two-dimensional quantum gravity. Now let's come to a seemingly different aspect, which is trying to formulate a quantum path integral over metric, two-dimensional metric, by discretizing space-time, as we do in gauge theories and as we do in other formulation of gauge theories. We assume that space-time is discretized in some sense. Okay, so the idea is consider discrete gravity by considering that instead of having a continuum space-time, we have some discrete triangulation, or as it's called by mathematicians, a random map. So for instance, here, our sphere, in fact, is made out of small triangles. It's an approximation. Small triangles that are glued together to make a two-dimensional surface. It's called a two-dimensional simplicial complex in mathematics. The idea is sum over all these objects. Okay? So there is a very simple observations. It is that the dual of this triangulation is a trivalent planar graph. It's a dual in the sense of you replace triangles by vertices and you join the center of the triangles. Okay, so you get a planar graph that is a trivalent graph in this case. So let's consider. And in fact, it's drawn on a sphere. So it's what the mathematicians call the fat graph. In fact, the propagator are ribbons. Okay, so this is, in fact, the graph of the theory that describes the sum of a triangulation. Okay, that's elementary topology. And, in fact, the combinatorics of planar maps can be studied by many, many, many different mathematical techniques. One technique consists in writing recurrence using combinatorics. We are counting objects, so we can make a relation between the number of different kinds of objects. And this, in fact, has been started a long time ago in the 60s by a well-known mathematician called Tutt. He was Canadian. In fact, I think he had a professor position in Toronto. It's one of the great combinatorists of the last century. But there is also another way to count these objects, which consists in observing that these diagrams that I draw here are, in fact, the Feynman diagrams of a quantum field theory whose fields are matrices. Namely, they are like gauge fields. They carry group indices. Okay? And this is an observation that was first done by Gerhard Toft, which shows that the planar limit of such matrix quantum field theory are the planar Feynman diagrams. He was interested in gauge theories, but you can use this just to count diagrams, to count triangulation. And this was initiated, in fact, not by Gerhard Toft, but by Brezin, Parisi, Itzigson, and Zuber. I'm going to speak about that. And they observe basically that if you construct a path integral where you integrate over a single matrices with this action, so there is a trace of m squared minus a cubic interaction terms, with a proper rescaling in the size of the matrix, then what you get is exactly you count exactly the planar trivalent diagram that I drew before. And you can use various techniques about integration of a space of big matrices to solve the problem and get equation, get the numbers. Okay? So there is a very long, very big literature on that. But one aspect that is interesting too is that if you are considering what's happening for finite matrices and classify all the terms in terms of a 1 over n expansion, this is a topological expansion. The leading term that counts for large n counts planar surfaces. The subleading terms count surfaces that have the topology of a torus. The subleading terms with 2. So this is the large n expansion is in fact an expansion in the topology of the surface. So an expansion is a topology. And these diagrams, in fact, if you count this integral, it has a critical point where the integral has some singularity, and this singularity is dominated by the behavior of large maps with a large number of triangles. And there is an interesting expansion, what you get if you take the limit when n goes to infinity and the coupling constant goes to G critical, because then you get large maps, and this coefficient n is replaced by a factor z, which is over the 1. So you get a sum over all possible continuous, sum over all continuum metric, weighting in a different, and getting a control on the weight of the different topology. So in other words, you get a sum over, this would correspond to diagram of string interaction, for instance. And if you are able to sum all the diagram of string interaction, you get a control of a non-perturbative formulation of string theory in some very special case, but And in order to do that, you have to, in fact, to know how this integral diverges when g goes to 3 kilo. And this depends on some exponent that is called the string exponent that I'm going to discuss a bit later. Okay. But the value of this string exponent come out from the solution of the matrix model. Okay, so you see the basic idea. Okay, so what are the names associated to this? Well, this is William Tutt, this is Giotto, this is Breza and Sixon. Well, the first idea to use this idea of applying this to two-dimensional gravity was done by Kazakov, by Ambjorn, Durus, and Fröhlich, and by myself. And these are the famous theoretical physicists, I think high-energy physicists know all of them, who had the idea of this double scaling limits that leads to a non-perturbative formulation of string theory. Okay, well, there are many, many other aspects of the theory that I'm not going to treat here. But I'm going to go to discuss one particular aspect of both discretized gravity in 2 dimensions and of continuous gravity that is called the KPZ scaling law. So consider that you have a quantum metric on the sphere. So it can be given by the sum of a possible triangulation. And on this, coupled to this gravity, there is some CFT associated to matter. And this CFT can be realized in a discrete model by, for instance, introducing an Ising model on your space and setting the Ising model at the critical point. Okay? And so the CFT has local operator. For the Ising model, it will be the spin energy, the local spin operator, and the local energy density operator. So those are the local observable. Okay? And the KPZ relation, KPZ holds for Knishnik, Polyakov, and Zamolodchikov, states that there is a relation between the scaling dimension of those operators in the CFT isolated, so the CFT on a plane, and the dimension of the corresponding operator in the theory where gravity is coupled to the CFT. And this relation is a quadratic relation between the dimension of the CFT and the dimension x. And it has this form, and it involves gamma. And remember, gamma is related to Q, so it's related to the interaction coupling in the Liouville. And so gamma is related to the central charge of C. Okay, so this is the first KPZ relation. There is a second KPZ relation that tells you how is the string exponent related to the CFT. And you take this simple form. This is a string exponent. It's related to gamma. That is related to Q. That is related to the central charge of the CFT. Okay, so this was proposed by Knishnik, Polyakov, and Zamolodchikov, and this was derived by this gentleman in 1981. This relation, in fact, was proposed by Polyakov and was derived a bit later by myself and by Dissler and Kawai. And basically, the idea is to use standard method on CFT and Liouville and to use the fact that the scaling dimension of a vertex operator is given by this relation. So I won't show you how it's derived. It's basically a standard CFT calculation. Okay. So here are the gentlemen, Knishnik, Polyakov, and Zamolodchikov, Dissler and Kawai, and those guys are mathematicians, most of them, that I'm going to associate to KPZ a bit later. Okay, and this KPZ, finally, is not this KPZ that Conos matter physicists would recognize immediately. Okay, so there are many evidence for the equivalence between matrix model formulation of two-dimensional gravity, namely discrete gravity, and the Liouville formulation of two-dimensional gravity, namely the continuum formulation of two-dimensional quantum gravity. Okay? So they have the same scaling dimension for the operator. Well, the observable obey the same called recursion relations that are generalization of the Tutter relation that allows to compute some of the observable. While there are also some other relation that comes out from considering a model of matrix model device by Kontsevich that is associated to the geometry of moduli space of Riemann surfaces. But, however, in fact, there is no complete understanding of the relation so for instance, one may ask, can we start from a discrete model and find a conformal maps, namely find a way to build a conformal gauge formulation of the discrete model? Another difficult problem that is poorly understood is the relation between the conformal structure, the structure of the surface as the Riemann surfaces that leads to the KPZ relation, and the Riemannian structure. What is the structure of this space as a space with a distance? Because in conformal field theory, there are no distance. You can perform scale transformation, so the meaning of a distance between 2 points makes no sense. But on the discrete formulation, and we expect in general in quantum gravity, we would like to have distances given by the length of geodesics. Okay? So, and except for a special case of pure gravity where C matter is 0, there are basically no results about what is the relation between those two objects. Okay, and let me give just an example. In fact, one can get some results of the distance geometry on random maps and random tree by using the fact that for, in fact, planar maps, there is bijection between planar maps and other combinatorial objects that are called label trees. So this was devised by mathematicians, by Corey, Vauquelin, and Schaeffer. But in fact, physicists like Ambjorn and Kawai came to the same results by a different path, combinatorics too. And just to give you just a flavor of what's going on, this is a tree. And there are some labels, some numbers that are associated to the tree according to some rules that I'm not going to describe. But there are rules that allows out of a tree and of labels to build a surface. And here is, for instance, the dual of a surface. So it's a quadrangulation. This is a dual of a surface made out of square instead of triangles, but that's the same, which is planar. And out of these results, in fact, one gets two results. One gets that if you just count triangulation or quadrangulation, the Hausdorff dimension of the surface, the dimension of this object considered as a metric space with a distance, is found to be 4. While the spectral dimension, this is the object that tells you how a random walks or a diffusion process on the surface scale with time, is 2. On a plane, on a flat plane, the spectral dimension and the Hausdorff dimension are 2. They are equal for very simple reason. Here, they are very different. So it means that random walk on a quantum metric is not very different from the classical one. It's definitely different, but it's not very different, while the geometry of geodesics on a quantum metric is very, very, very different from flat metrics or just classical metric. Okay, yes? Pardon? This is for pure gravity. And we expect, I'm not sure they are proof complete, but these results should hold for gravity coupled to any matter field. Why? This is a result for pure gravity. And there are there are some hints of results for the other models, but it's definitely different from 4. But there are no exact results or proven results. So it's mostly terra incognita or some big ocean, and there is one island where we sit. Yes? Sorry?
Do all the edges of the triangle have the same length by some?
It doesn't, yes, yes. Yes, so it's some kind of Regge calculus made out of triangles with the same length. Yes, yes. Or they may be slightly different, they may fluctuate, you may play with that, but basically they have the same order. Yes. So it's very different from Regge calculus. There is curvature associated to this diagram. Okay. And let me, I don't know if I'm going to have the time, but okay. So now, I have something. Let me consider, go back to Liouville and consider the local limit of Liouville. So if you consider a surface described by Liouville theory, locally, if you look at what's going on near a point, in fact, you can forget about the exponential interaction term and consider that the metric is just the given, the exponential of a Gaussian free field, which makes things simple. And the Gaussian free field is already something quite non-trivial and interesting. For instance, it was shown, this is an example of a calculation done by Oded Schramm and Scott Sheffield. If you consider what are the level lines of a Gaussian free field, so you have a Gaussian free field here, it has boundary conditions here and here that are different so that there is a unique level line, it's some fractal. And it's a very interesting non-trivial fractal that is related to a gross process called SLE4 that I'm going to describe later on. Okay? So what is this SLE process? This SLE process is a gross process, so a law to define how a curve can grow in the plane. That has two properties. It is conformally invariant. It has a property that basically is a generalization of a Markov property that is called the domain Markov property. And in the upper half plane, it is just defined by a very simple stochastic equation. We consider a function g of z that depends on the variable that is the time. And as a function of time, the variation of the function gt for a given g is 2 divided by gt of c minus a stochastic variable that corresponds simply to a Brownian process, so it's a real number. It's a Brownian process with an amplitude that is proportional to the square root of some parameter kappa. Okay. So this very simple equation for a given t defines a conformal mapping from the upper half plane minus some curve to the upper half plane that I'm going to describe later on. And this process was invented by Oded Schramm in 91, and this became a huge field in mathematics. So this Oded Schramm unfortunately died in 2004, I think. But, okay, so let me draw. Okay, so this is the original z plane in the upper half plane, and there is, in fact, it appears that there is a curve in this half plane defined by this stochastic process. And when I map z into w equal gt of t, what's going on is that, for instance, this blue curve is squashed on the line, on the boundary of the upper half plane. So this point is mapped into this point is mapped onto this, and so the right-hand side and the left-hand side of the curve are mapped either here or here. But the remaining of the curve is still there. So if you go now to a larger time, this curve will be mapped here and this curve. Okay. And basically, the curve gamma of t is a set of points that, along this evolution, crashes on the plane. Okay. So this is a seemingly simple gross process because you can invert the process and say that you start from this and you start to draw a curve according to the SLE equation. But this seemingly process is highly non-trivial. First, it defines a curve that is in fact a random curve. It's a fractal curve. It has some Hausdorff dimension. And its Hausdorff dimension depends on the parameter kappa, namely the amplitude of the driving force that is a Brownian motion. For kappa is less than 4, it's a simple curve. For kappa between 4 and 8, it's a curve that can hit itself. And so it has an interior and an exterior. And for kappa larger than 8, it's a space-filling continuous curve. So it's a curve like the piano curve that fills the whole space. And so the Hausdorff dimension of this object is 1 plus kappa over 8, and it's 2 if kappa is larger than 8. And this result is non-trivial, and it takes many years to the mathematician to understand what was going on and to prove it. Okay? So what is the relation between SLE and the Liouville theory and two-dimensional gravity? Okay. So SLE, in fact, was a way to study random fractal curves in the plane. And the interest is that there is a relation between the SLE curves and the interface of critical systems, like the interface and the clusters of the two-dimensional Ising model. In fact, the SLE curves are the continuum limit of the interface of critical models in 2 dimensions. This was the idea of Oded Schramm. And moreover, there is a very simple relation between the central charge of the CFT that describes the continuum limit of this critical model, like the Ising model, and the parameter kappa that characterizes the SLE curve. And this relation, here it is. This is the relation between kappa and the central charge of the corresponding CFT. And this relation is very much like a KPZ relation for some Liouville theory coupled to the CFT, because this coefficient square is just the Q squared of some Liouville. So this relation suggests. Pardon? Yes. I mean just that you take the Ising model, you take, for instance, in a box like that. Well, here I have plus spins. Here I have minus spins, so there must be an interface. And this interface is a fractal object. Yeah. In order to construct interface, you have to put interface. But if you go back to the Ising to the SLE process, you know, in this SLE process there are 2 singular points in the half plane, 0, the starting point from my SLE, and in fact infinity up. So in fact there is also some interface with a boundary condition with 2 singular points in SLE. And that's the relation. For instance, the SLE for some value of kappa will correspond to having plus spin here, minus spin here, and some interface. Okay? So there seems to be a relation between SLE. Okay. So now, in fact, there is a relation between KPZ and the Gaussian free field. Because mathematicians like Duplantier, Sheffield, Benjamini, Schramm, and Rod and Vargas have shown that you can find a KPZ relation between the fractal dimension of some object in a classical space and the fractal dimension of this object in a random metric that is of the form E gamma, some Gaussian free field or something like that. Okay. And that's, so consider a fractal object that has a dimension D naught. For instance, this is a fractal object that has dimension D naught in flat space. Now, add to this flat space a random metric of the form E gamma phi, a random measure, in fact, E gamma phi, and compute now the fractal dimension of this object with respect to this measure. So you weight in a different way the different element of the fractal. So in general, you will get a different result for the fractal dimension of this object, D. The relation between D and D naught is given by this formula, which, in fact, is nothing but the KPZ relation for this object. Okay. So KPZ-like relation holds in a more general context than just quantum gravity in 2 dimensions. And there is an overlap between those 2 results, but this geometric formulation of KPZ gives information on things that have no correspondence for 2-dimensional gravity. Okay. And in fact, you can show that by, for instance, either using probability theory or using random walks in the quantum metric. And perhaps it's a good point to show you a quantum metric, because I have not showed what is a quantum metric. So she shouldn't have started. Okay, so let me start. Yes, so this is the E, the exponential of a Gaussian free field for a value of kappa of 2/3, the corresponding kappa in the, so this is gamma equals square root of 2/3. So in fact, it corresponds to coupling two-dimensional gravity to a theory with central charge minus 24. So this means we are in a regime where the quantum effects of the quantum gravity are not very large. But nevertheless, this is the value of the density. This is exponential gamma g. And you see that there are some points where it's very big and some points where it's very large. So the quantum metric is already quite spiky. Okay. And so here is a typical aspect of a quantum matrix in 2 dimensions. Okay, and this is just to show you, this is what's happening to the quantum. If you perform a diffusion process on this quantum matrix, this is how it lays. You start from a single point and you have a relaxation. So this is equivalent of a heat kernel computed in a Gaussian matrix. Okay, and now I'm giving the same thing for strongly coupled gravity. The metric is even more peaked, but the diffusion is not that different. So that's what I meant by saying that a random walk in a quantum metric is not very different from a random walk in a flat metric. Okay, so now more about the relation between SLE and Liouville. So how can one explain this relation between SLE and Liouville? Well, the idea that has been pursued by several authors, not only Dubeda and Kupienen, but in fact the nicest formulation I know comes from idea by Scott Sheffield and has been formulated cleanly by Bertrand Duplantier and Scott Sheffield. The idea is that out of a Liouville field theory treated as a Gaussian free field, you can construct an SLE in the following way. You take a Gaussian free field in some half space, for 2 half space, you glue them in the conformally invariant way, and you obtain an SLE. So let me explain. This is a very sketchy presentation. Imagine that you have a sheet of paper with a flat matrix, and simply you have a cut. There is a half line cut in it, and you start to glue it so that the distances, the metric is smooth when you glue it. Okay, so what you are performing is that you are gluing, well, this goes in that way. You are performing classical welding or zipping of a flat metric. You get just a line here. You start from this, you glue it, you get this. So you get some kind of fractal, but a trivial fractal. That's just a line with dimension 1. Now, do this for a space where here you have a quantum metric given by the exponential of Gaussian free field with a coefficient gamma, enforce free boundary condition on the boundary of this space, so that, in fact, the length elements are different here and here, and find a conformal transformation so that the lines elements are mapped together and coincide so that the metric is smooth on the resulting. So that's the analog of zipping a plane with a cut, but it's called conformal welding. And that's something that is a tool that is very well. Okay. So if you do a conformal welding from the original point here to here, okay, you get another thing. And here you get some fractal curve. Well, one can prove that this fractal curve is nothing but an SLE. An SLE characterized by a kappa parameter, and kappa is related through gamma by kappa equal gamma squared. Okay? And so this is an example of a relation between a quantum metric, and SLE. You can construct a SLE curve out of quantum matrix by gluing pieces of plane. Okay. And the fact that there is here some angle is due to the fact that you have some vertex operator, some operator here, and I've seen that, if you have some operator here, it amounts to insert some conical singularity in your Liouville theory. So that's why there are some kind of cones or wedges that are called quantum wedge by Scott Sheffield. Okay. So now, let me go back to one last point that I want to explain. That is, how can we try? So, well, everything I said here was in the continuum. So, now we have a much more precise idea of the relation between two kinds of random objects or quantum objects defined in the continuum: quantum gravity, quantum matrix, if you want, and SLE curve, which are both defined in the continuum. Now, let's go back to the original, one of the original formulations of two-dimensional gravity. That was discrete two-dimensional gravity, random lattice, random triangulation, or random maps. Okay? So, how, the idea, can we embed a random map onto the plane or on the sphere by preserving, in some sense, its conformal structure? So, in order to make a discrete version of the conformal gauge fixing of Polyakov. And can we show that we recover the Liouville theory out of this purely discrete combinatorial problem? Okay. So that's the basic idea. So go from the, so in some sense, can we build out a continuum limit of random maps that preserves the conformal structure? Because that's not what matrix models do. Okay. Well, so here is, for instance, a three-dimensional representation of a random. So this is a random triangulation. It's represented by some algorithm in 3 dimensions, but you should view it as just a purely combinatorial object. And you see that it's clearly very different from a plane. Okay. And how can you map it in a conformal or quasi-conformal way? Quasi-conformal, that it's not exactly conformal, but you get a control of the amount of non-conformality, if you want. There is a mathematical definition of that. But, okay? So one way is just to use the uniformization theorem of Riemann, basically, that tells you that for any Riemann surfaces like that, you may consider that those are equilateral triangles, and on the vertices there are curvature defects. So there is a metric, and although this metric is defined out of discrete elements, you can use uniformization and map it in a conformal way on the plane. So this is well, an exact uniformization. The line will be curved, but so this is not exact, but that's an approach that is pursued with some results by Nicolas Curien, a young mathematician in Orsay now. Now he's in Orsay. Okay. So that's one idea. Just use the exact mass of conformal mapping. Now, another idea is to use, what's going on? It's not working anymore. Okay, no problem. Is to use circle packing. So, this is a circle packing. A circle packing basically is just a dense packing of circles in the plane. And there is a beautiful but old theorem that says that any triangulation, basically, up to some subtleties, any triangulation can be represented as a circle packing, where each circle represents a vertex. So the center of the circle represents a vertex here. Okay. So that's something which is an idea that has been advocated by many people. So I call it folklore, because many people have been saying we should do that. But I'm not really aware of precise results obtained using this procedure. Also, it seems very attractive. So perhaps it's just that I'm not aware of the right literature, or simply people didn't have the correct idea. It should work, but it doesn't work. So let me finally discuss a little bit seemingly related idea that I've been pursuing with Bertrand Hénard in Saclay. So the idea is to use another form of quasi-conformal map, whose idea is using what is called Delaunay circle pattern. So the idea is to associate to this triangulation another triangulation that is built out by the Delaunay procedure. You are given a set of points, and out of this set of points, you are constructing the neighboring of all the points that are closest from one point than to the other one. And you construct out of that the Voronoi complex and the Delaunay triangulation. So that's very, very classical geometry. Well, 19th or probably even 18th century geometry with triangle in the plane. And again, there is a theorem that tells you that there is a class of triangulation that can be mapped into such Delaunay pattern. I call circle patterns because Delaunay are associated to angles circumscribed to triangles. So there are some circles also, but not circle pattern. It's a different kind of, it's not a circle packing, it's some circle pattern that is a different. Okay. So the idea is that now that we can perform a bijection between a triangulation to which and to each edge we associate some angles, and we can map this abstract object that is a random triangulation with some random edge angles, which in some sense is a triangulation of some space that is the moduli space of puncture sphere with n vertices, where n is the number of vertices of my triangulation. And there is a bijection between this object and an object that seems very easy, which is the space of random distribution of n points on the plane, out of which you built a Delaunay and Voronoi complex. Okay, but of course, when you go from this to this, you get a non-trivial measure on this distribution of points. And the idea is, can we prove that this non-trivial measure is related to the Liouville theory? That's a work in progress. I must say that we have some idea, but we have not a definite proof. Okay, and let me just show you, since this is a very general seminar, just qualitatively what is going on. So we have a measure on points. So we imagine that this is a sample of points that lives in the plane, and out of this sample of points, we have constructed a Delaunay triangulation, some specific triangulation, which is uniquely determined from the set of points and which satisfies some property. Now, we expect that, in fact, because the whole process, in fact, is conformally invariant, when you sum over the density of points, you may have large fluctuation into the density of points, and this will correspond to having abstract triangulations with very fluctuating topologies, not topologies, but geometry. So, for instance, this is a triangulation built on the plane, and this is the abstract corresponding triangulation represented in a three-dimensional space. So this is the real thing. This is an abstract representation of this object, where basically here the distance between the points can be very small or very large, and basically here the computer program has tried to make them all of the same order. That's what it's doing. Okay. And now let's see, for instance, what's happening when half of the points collapse. What's happening to the corresponding triangulation? Hop. Half of the point collapse, and the surface the corresponding triangulation gets pinched. And this is a typical fluctuation that is allowed up to some degree in the Liouville theory. So you see that we expect, if the measure on this metric is given by Liouville theory, to have a huge fluctuation of the number of points that we are trying to control it mathematically. Because this is just a very general picture, but we can formulate this in a mathematically proper way. Okay, so now one final point I want to discuss. All this is quite recent stuff, and the last 2 points are points where I have contributed in a marked way. This is, can we go from the simple GFF, so Gaussian free field, to Liouville theory? All the results I have been discussing or presenting that are mostly not of mine, about the relation between Liouville theory and SLE, for instance, are obtained in the approximation where you just take as a quantum metric the exponential of a Gaussian free field. And in the real two-dimensional gravity, the quantum metric is not the exponential of a Gaussian free field, it's the exponential of a field that is given by the Liouville action. That locally looks like a free field, but at large distance, it's not a free field at all because it lives in a surface with negative curvature. Okay. So, and all the beautiful results that have been obtained in Liouville theory by CFT method relies on the fact that we assume that this theory exists, that it has the property of a CFT, and then we use the beautiful machinery of CFT and integrable system and conformal bootstraps to compute things. But does this theory exist? Well, every physicist will tell you, of course, it exists, because we can compute with it, but mathematicians, they say, no, we need to construct it. So, a recent result by Rémi Rode and Vincent Vargas, who are mathematicians, Antti Kupiainen, with a physicist in Helsinki, and myself, is a rigorous probabilistic construction of the functional integral and the correlation function of the full theory, Liouville theory, so with the mu e gamma phi term, on the sphere as the first step. So in other words, we are able now to construct in a way that satisfies a pure mathematician who wants the proof with limit epsilon goes to 0 of this object. The object where you have a sphere, a quantum metric on the sphere, and a set of vertex operator or puncture singularity inserted so that this object is well defined. So we are able to compute the objects that correspond to the correlation function of some vertex operator in the Liouville theory, defined for mathematicians as the expectation value of a complicated random variable constructed out of a Gaussian free field phi. And with this, we are able to prove that this object limit. We are not able to compute it exactly, well, but we rely on the result of conformal field theory for that. But we are able to show that this object exists and it is conformally invariant. In particular, with the scaling dimension here, it satisfies the KPZ relation. That holds for the full-fledged Liouville theory and not only the simple limit that is the Gaussian free field. So this locally here, somewhere here, the field is a Gaussian free field, but globally it's not a Gaussian free field. It's a Liouville theory, a complicated, highly non-trivial interacting theory whose background is determined by the interaction itself, as you expect in any quantum theory of gravity. If there is some effective background that emerge from the quantum theory, it's determined by the theory itself. It's not given by some God. Okay. And, yes? Pardon? Between phi? Yes? Well, the point is that simply, if you consider, for instance, correlation function of vertex operators that are very, very close together, while the size of the surface is given by 1 over mu, then you can approximate it by a Gaussian free field calculation. So locally, the correlation function of these quantum fields looks like the correlation function of some Gaussian free field with proper boundary condition, but only in this limit. Okay? Yeah, no, we have relation because, in fact, we start from the Gaussian free field, and this is a non-perturbative construction of some perturb. So we add the interaction here. In fact, we add the interaction term, but we do not add it in a perturbative way because we cannot really perform perturbation theory except in some very special case. But we are able to treat it non-perturbatively using big theorem of probability theory that I'm not completely understand, but my three collaborators have much more experience into that than me. And we are able to give a construction non-perturbative in the sense that we do not expand in mu, and we do not expand in mu because mu is not really a coupling constant. If you think about it as a coupling constant, the problem is that the size of the surface is given by the inverse of mu, so you can never treat it, well, except in some limiting case, as perturbation parameter. So the only way to construct it really is to construct it in a non-perturbative way. Okay? So this is very recent result. That's mostly mathematician because no physicist, including me, will say this is a big surprise that this object exists. But I think it's a very nice results because now we have the right tool to be interested in other non-trivial objects, like for instance, Liouville theory on the disk, and to try to give a formulation, for instance, of conformal welding for the Liouville theory and not only the Gaussian free field. Okay, so, and this is the paper. It has just been issued on the archive 2 weeks ago, and with big words, and in fact, it's a quite long paper. And I hope that I just give you an interesting view of why the subject is interesting, why two-dimensional gravity is interesting, and not only for string theory, which is its main domain of application up to now, especially in high-energy physics and in theoretical physics, but in other fields. So thank you.
So, questions?
So one question is about, you talked about this random, what would you call it, set of points in the sphere. You know, you talked about a probability distribution over sets of points in the sphere, which you tried to relate to the random triangulation.
These special points? You mean in the discrete formulation?
A point process in the sphere? Yeah, a point process in the sphere. Yeah, in the discrete formulation. Near the end, if you go back, you'll...
Okay. Tell me where I have to stop.
No, keep going forward, I guess.
Pardon?
Forward. Go back. Go forward. Didn't you? Maybe it's this one. You talked...
Here or here?
No.
Here?
No, I think maybe the one on the left, if you like. But
yes.
Didn't you talk about some probability distribution over sets of points?
Yes.
That's what I'm asking. So, and then you said you wanted to make it conformally invariant.
Yes.
So are we talking about some n going to infinity limit in this case?
In fact, in the model I've been studying with Bertrand and R, to each distribution of points, so imagine that before you have this triangulation, you have just points. And out of the triangulation that is constructed here, you construct a probability distribution. So the probability distribution is a function that is a complicated function that depends on the position of all the points. So it's not a local probability distribution.
So it's not like the Delaunay.
It's something more complicated.
It's more complicated.
In fact, it's given by the determinant of some matrix that you construct out of the distribution of points. And in fact, this metric is a Kähler metric. Okay. And so this distribution is conformally invariant. It means that if you make a conformal transformation from the plane into the plane, you get the same measure. And you cannot have this with a distribution probability that depends only locally on the position of the points. But you can obtain this if you have a probability distribution that is defined globally for all the points. And that we have. That's what we have.
But is the number of points fixed, or is it?
At the level
is the number of points itself a random variable, or is it a fixed number?
You can make it a random variable, but you can compute with a fixed number of points.
And you get full conformal invariance with a fixed number?
Yes. The conformal invariance is valid if you have a fixed number of points. Therefore, if you now make the number of points fluctuates, it will still be conformally invariant.
But it seems strange because the points themselves have only a finite number of degrees of freedom.
Yes, but still,
whereas the metric has
it is conformally
the metric
invariant.
should have an infinite number of degrees of freedom.
Yeah, here the metric has a finite number of degrees of freedom, but it is still conformally invariant. I can show you the...
Okay.
Yeah. I can show you. That's a technical point, but that's one of the beautiful features of this model.
I have another question.
Were there other questions? Okay.
Bouncing back. So this is a question that I've always been confused on, although I think I've said that there's an answer. In fact, yesterday I was talking about this with Nosipiwo, a student here, and I told her this. Did I tell her a lie? So the following, this is what I told her. I told her that in three-dimensional gravity there are no local degrees of freedom, which is true, right? That I think is true. In two-dimensional gravity, naively, in the classic, if you look at it classically, there's an infinite number of degrees of freedom. I mean, basically, what you showed us, that the Einstein tensor vanishes identically. So there are no equations of motion.
Yes.
Unless you put a cosmological constant, in which case there's no solution.
Yes.
So it's a completely degenerate theory. Yet I thought that in the quantum version, which is what you've been talking about, that in some sense it's a field theory again with no degrees of freedom.
Yes.
On the other hand, the Liouville theory has a huge number of degrees of freedom.
Yes.
So what's the physically, is it correct to say physically that there are no degrees of freedom, no local degrees of freedom?
Yeah, no, I think your point of view is not incompatible with what I say. Because, as you say, the quantum gravity with two dimensions with no cosmological constant has an infinite number of degrees of freedom. If you have a cosmological constant, I think, in fact, it has no degrees of freedom because there are no solutions of the equation of motion. And in any case, it's only when you quantize the metric that it becomes a theory with an infinite number of degrees of freedom, which is the Liouville field. But nevertheless, when you compute correlation functions of the Liouville theory, they can be related to models of two-dimensional gravities that are topological, that can be formulated in terms of the Kontsevich random matrix model. So in fact, you have a theory with physical degrees of freedom, the Liouville field, and when you compute this correlation function, at least some of their correlation functions becomes topological, in the sense that they are the correlation function of some topological field theory. I don't know if I am very clear, but that's a picture I have. Or if you prefer, you can also state that. You can state that if you stay with a two-dimensional quantum gravity, there are no local degrees of freedom. You can define only global degrees of freedom. And in two-dimensional gravity, there are very, very few global degrees of freedom, which are the topological degrees of freedom of the theory. So the local degrees of freedom that are the degrees of freedom of the Liouville theory, in fact, are not observable from the point of view of a two-dimensional gravity observer. But once you have fixed choose a particular gauge, then these degrees of freedom are observable. They are gauge dependent. They are observable in a definite gauge. And they are interesting because they are related to, for instance, the physics of this SLE process, the physics of this interface, etc. So in some sense, I'm viewing it as they are depends on the gauge, and they decoupled from the purely gravitational degrees of freedom that have to be topological. I'm not sure I'm correct, but that's the picture I have. Okay?
Okay. Are there any more questions? You have another one?
This is the last. So this is all in a Riemannian metric. What's known about the analytic continuation to the Lorentzian metric?
Very little is known, at least for me. I know that in the Liouville theory, people have tried to define the Liouville theory in Lorentzian framework, but you can do it on the cylinder, for instance, or on the, if you consider that the sphere becomes a cylinder, then this can be done. But as soon as you go to surfaces with higher genius, you get into trouble simply because, as usual, if you have a surface that splits, it's a singular process in Riemannian time. So I think little is known. From the point of view of the application of Liouville theory to string theory, I don't think it's a problem because, in fact, the signature of the worldsheet is not very important. What's important is the signature of the external space in which the string lives. So you may very well have a string with a Riemannian signature propagating in a space with Lorentzian signature. Because the fact that you have a metric, an external metric with a Lorentzian signature is just a particular solution of the equation of motion of a string. So that's the first point. The second point is that from the point of view of the application to CFT, that's not really important either, because in CFT, the application first in the application in condensed matter, one usually deals with statistical systems. There are some applications to one-dimensional quantum systems which are really Lorentzian, but again, in a conformal field theory, one can perform a Wick rotation very easily. The analytic structure in space variable of the correlation function of the CFT and of the operator, they are all analytic functions of the Z. So the Wick rotation is guaranteed from CFT. Okay. And finally, for the last results that have been presented, we are really working in a Riemannian space. We are not looking at what would happen in Lorentzian. So all the last part was in a plus-plus signature.
I was thinking of the third application that you didn't. What? The third application, which was to quantum gravity, 2D quantum gravity.
Yes.
There the Wick rotation, I mean, there the signature is important.
Yeah.
Okay, maybe let's thank the speaker again.
Okay, thank you.